Okay, so in this discussion, we'll be talking about what happens to our linear elasticity when our solid is anisotropic. We have only discussed cases until now where the solid was isotropic. However, many materials like crystalline solids or composites are actually anisotropic in nature. So in this particular discussion, we will see how linear elasticity applies when the solid is anisotropic, meaning it has the elastic response is different along different directions. Okay, in isotropic, the elastic response was same along all the directions, and we had, I think, earlier seen an example how a foam and steel can be combined to form an isotropic solid. Okay, so say if you have a simple okay, or let me directly draw it like this. Say if you have a solid in which uh, the most general case would be that the elastic response along any two directions would be different from each other. However, it is found that many a times there is some sort of a symmetry in most of the solids which are occurring, and that gives us an advantage to somewhat simplify or ease our application of linear elasticity. For example, if you have a simple cubic uh, crystal, these two directions give the same elastic response. Not a third direction, obviously, but these two black directions will give you the same elastic response. Similarly, if you have a hexagonal crystal, you may have learnt about these things in a course in material science. These three directions will give you the same elastic response. Okay, so the arrangement of atoms in such solids is in a way that the response is same along these directions. Now, if you have a fiber reinforced composite, I mean, for example, consider the case of concrete and these steel bars which are used to strengthen. In a solid like this direction and this direction will have the same elastic response. Okay, so these are basically the arrows show material symmetry directions. It's because of the properties of the materials itself. Like a simple cubic crystal has atoms arranged in a way, and hexagonal system has the atoms arranged in a way that these three directions give the same response. Okay, not a fourth direction, say like this. Only these three black directions. Okay. Similarly, in this fiber reinforced composites, if the fibers were lying along, say something like this, then these black lines will not have the same directions. Okay, then the symmetry may lie in some other direction. So it depends on how exactly the fibers are aligned. Okay, so we will take advantage of this fact. Okay, so And there's a principle called the Neumann principle, which actually says the same what we have just discussed. The symmetry in material microgeometry corresponds to identical symmetry in the constitutive response. Okay. Okay, so it can also happen that the material has some sort of a curvilinear symmetry, in the sense it's not Cartesian system based. That happens in, say, a bone or a wood. Both of them have similar sort of a structure, and hence they will also, because there is a similar material structure, and they will also have a similar material response, in this case linear elastic. One of the points which you should be knowing is that the properties of any material, say in this case we are referring to mechanical property, but it can be electrical property, optical property, whatever be it, depends on the structure of the material, and hence it's called the structure and properties of a material, the overall domain of material science. So the guiding idea is that if you understand the structure well enough, you can easily do things about its properties. In this case, obviously, our properties of reference are mechanical properties. It could have also been thermal properties or thermomechanical properties and so on. But that's the basic idea. Okay. So let's see, we had this Hooke's law, which wasCijklekel. Okay. The idea was that this would be valid at any point in a solid, okay, irrespective of the fact that the material is isotropic or anisotropic. The logic was that every component of stress at this point of reference is linearly related to every component of strain, and hence if you expand it you would get 9 terms, and henceCijkl was this uh, matrix or the fourth order elasticity tensor, which had 81 components. Okay, of course, for an isotropic form we had shown that we had taken a general form with only two independent elastic constants, but this is what is it in the most general case, 81 components. Now there were certain symmetries which we had learnt about before. For example,Cijkl is equal to Cjikl, and this is equal toCijlk, and this is equal to Cklij. Okay, so this, if you remember, was because of the, this particular relation was because of the symmetry of the stress tensor. The stress was symmetric because the moments were being balanced, and that was happening because there was no angular acceleration of the point which we are concerned with, this point. Okay. Similarly, this particular relation, in the sense isCijkl is equal toCijlk, was because of the symmetry of the strain tensor. This was there because of the geometrical arguments which we had made during the geometrical construction of strain theory. And this last part, Cijkl is equal to Cklij, is actually due to the arguments which we had made in the strain energy discussion. Okay, now we started off with so-called 81 components, but eventually we had shown that there were only 21 independent components. Okay, so this reduces the original 81 independent elastic constants within Cijkl to a set of 21 elastic moduli for the general case. Each of them can clearly take up some distinct values. I mean, let's do that calculation, though we have done that before. We had done it in a different way, but you can also do it in this way. For example, sorry, Jikl, okay, the first relation. Now this had obviously 3 into 3 into 3 into 3, 81 components. Now in this case, L can obviously take 3 values, K can take 3 values, but because this Cij is the same as Cji, see how many components would be there. If you don't want to do it the hard way, the easy way is to just write it as C11, C12, C13, C21, C22, C23. So we are just taking this ij1 because KL is the same. So I'm not writing KL separately. 31, 32, 33. Now because this is the same as this is the same as this, and this is the same as this, you will be left out with 6 components. Okay, so this 2 combined can take 6 values. That makes it 54 constants. Okay, just this first symmetry relation. Okay, now you apply the same logic to Cijkl and Ijlk. This would also have 54 components because here Ij will remain the same and Kl and Lk are interchanged. But when you see both of them being combined and sort of both of them applied, then this would only have Cijkl, because this can take only 6, this can only take 6, so you will have 36 constants. Okay, and even among this, Ij as a whole can be interchanged with Kl. Okay, so that would mean that, so if you take this as CAB and AB can be interchanged, then you can write these 36 components, and then the symmetric parts would go away, and then you would only have 21 elastic constant. So this is something which we had seen when we had discussed um, uh, strain energy density. Okay, so the original 81 independent elastic constants within Cij Kl to a set of 21 elastic moduli for the general case. Okay, this is still valid when the material is anisotropic. Reason: this requires only the symmetry of stress tensor, this requires the symmetry of strain tensor, and this is due to the existence of the concept of strain energy density. Okay, so all this has got nothing to do with whether the material is isotropic or anisotropic. Okay, An assumption which we are making is that the material is homogeneous, and the implication of this is that if this is your solid,Cijkl at this point and some other point will be the same. So the elasticity tensor does not vary with space. Okay, at all points on this you will have only these 21 elastic constants which will define the response of the material point. So you can invert this relation sigma ij equal toCijkl and write it as Eij is equal to Sijkl sigma kl. Okay, we have already done this inversion for a isotropic solid. Okay, but you can also do it for a anisotropic solid. I mean, in this form in which isotropy does not exist. We had discussed when we were discussing thermomechanical loading. Okay, so we had written, because our starting point was that the strain can be added as the mechanical and thermal because it can be superimposed, and then the strain was inverted to write the stress back. Okay, so the same concept can be applied, and this Sijkl is called the compliance tensor. Okay, and because it is a tensor like the elasticity tensor, it follows the transformation property. It has to. That's the only reason it's called tensor. Okay, so this can be somewhat confusing in the sense the stiffness is shown by this tensor C. Okay, and the compliance is shown by this tensor S. So the first alphabet of stiffness S is not actually S but C, and first alphabet of compliance C is not actually showing up over here. So this is just some confusion which was created, I think, intentionally, or perhaps attention was not paid. However, we have to follow that, we have to carry this burden, and we have to call this as the compliance tensor, because just about every textbook you will ever see, or every paper you will ever see, will have the elasticity tensor written as in terms of C. Okay,Cijkl. Okay, and we had also seen that because of the symmetry of stress and strain, you can reduce it to these 36 components. So we have the so-called Voigt matrix notation, which, so we don't have to write all those 81 components, even though many of them would be symmetric. So let's see what that is. You write C11, C12, C13, sorry, C14. Okay, then there are all the terms which I'm not writing, and then you could have EX, EY, 2EYZ, 2EZX, 2EXY. So you have sigma X, sigma Y, sigma Z, tau YZ, tau ZX, tau XY. Okay, so this is the so-called Hooke's law, which is written for a general anisotropic solid. We have still not included the symmetry of this tensor because of the strain energy density, but this is just to show the notation. Obviously, this is the same as this and so on, so it would only have 21 components, but we want to write it like this for now, so that we can write it in the shorthand notation of sigma I is equal to Cij Ej. Okay. So clearly sigma 1 is equal to sigma x, sigma 4 is equal to tau yz, okay, and E4 is equal to 2 EYZ, and E2 is equal to EY, and so on. Okay, so I hope this is easy to see. So in reality, as I've said, 21 independent constants only. Okay, because when you include the existence of strain energy concept, so we have seen that proof. If there is any doubt, please don't hesitate to go back and check. Okay, now obviously if you are writing the elasticity tensor in this form compared to this so-called 9 by 9 system, okay, there would be some relations which would exist, say between C11 and the other in the fourth order, this sort of thing. Okay, so I will write out that relation and then show what should be the relation. So in the fourth order scheme, this would be 1 1 2 2 C 1 1 3 3 C 1 1 3 1 and C 1 1 1 2. Okay, and then you would have 2 3 4 5 6. This would be C 1 2 1 2. This would be say C2 2 2 2. Okay, and then this can be written as C3 3 3 3, C4 4 8 3. Sorry, there's one more. C1 1 2 3, C1 1 3 1, C1 1 1 2. Okay, so you would have this as C4 4 4. So there is no C4 4. I'm sorry. C2 3 2 3, C3 1 3 1, C1 2 1 2. Okay, and then there will be terms over here, there will be terms over here, there will be terms over here, and there will be term over here. So let's see how this has come up. So let me write these two expressions. Sigma I is equal to Cij Eij. Okay, and that would, let me write the other one, sigma ij equal to Cij Kl Ekl. Okay, now if I write this term for, let me take up the first one, which is sigma x. Okay, so sigma x would be equal to sigma 1 1 according to this convention, and that would make it C11 Kl Ekl. If we write this in the expanded form, we get C11 E1L E1L plus C11 2L E2L plus C11 3L E3L. Okay, C11, sorry, C11 1L. Okay, yes. Okay, so now each of these terms can be expanded, so that would be E11 plus C1112 E12 plus C1113 E13 plus C1121 E21 plus C1122 E22 plus C1131 E31. Sorry, this should be C1123 E23. Okay, and then the last term would be C1131E31 plus C1132E32 plus C1133E33. Now expand on this side. Sigma x over here would be sigma 1. Okay, so that would mean C1j, sorry, this is EJ only, the void notation, EJ, that would be C11E1 plus C12E2 plus C13E3. Okay, fine. So now since sigma x has to be the same on this side, look at the coefficients. E11 is the same as E1, so this quantity is the same as this. E22 is the same as sorry, this should be C12 is this one, because E22 is the same as E33. Okay, and E33 is this quantity C13. Okay, that's done. Now okay, now we want to write some of the other terms. Okay, I'm sorry, this has to go all the way to 6, right? I shouldn't have stopped over here. This is actually C, because here it can go to 6. Both I and J go from 1 to 1, 2, 3, 4, 5, 6. Okay, you can see that over here there are 6 terms. Okay, so plus C14E4 plus C15E5 plus C16E6. Okay, now what is E4? E4 is 2 times of EYZ. Okay, so I will write it as 2 times of EYZ. What is C5? 2 times of EZX. 2 times of EZX. And what is E6? 2 times of EXY. 2 times of EXY. Okay, now I want to write, if I want to relate these two, I must write EXY as E12. So I'll write it as E12. I will write this EZX as E31 and EYZ as E23. Okay, fine. Now I'm coming back to this side again. In this one, the strain tensors are symmetric. Okay, that would mean that this quantity and this quantity are the same. Okay, so similarly E13 is the same as E31 and E23 is the same as, sorry, E32 is the same as E23. Okay, this would mean that C1112 E12, sorry, so E12 is over here, I guess, this one. Okay, so we can say that 2 times of C16, now we want to combine these coefficients, so 2 times of C16 is equal to, or C16 is equal to C1112 equal to C1121. Okay, then is it correct? C1112. hold on, let me just check if everything is okay. Yes, it is okay. And C15 will be equal to E31, C1131 equal to C1113. Okay, and similarly C14 will be equal to E23 is over here. That would be C1123 equal to C1132. Okay, now you can see that C11 is equal to C1111, C12 is equal to C1122, okay, C13 is equal to C1133, C14 is both equal to C123 or C1132, okay. So this can be written, and C15 is C1131 and C1113. Okay, and similarly C16 is C1112 or C1121. So that's how you can see that the relationship between this void elasticity tensors, which is Cij, can be related to the general Hooke's law, which isCijkl elasticity tensor. And this I have done for the first row. Clearly one can also repeat this exercise for the second row as well. So let's try to do that again for this second row. Let me remove some of these things. We'll write at least some of these terms. Okay. Okay, so the objective now is the second row, which is what, sigma y. Okay, so sigma y is clearly sigma 2, that is C 2j ej, that is equal to C21 E1 plus C22 E2 plus C23 E3 plus C24 E4 plus C25 E5 plus C26 E6. Okay, now sigma ij is so in this case this would be sigma 2 2. Okay, sigma y would be equal to sigma 2 2. Here sigma y would be equal to sigma 2. That would make it C22. Each of these terms can now be broken. C22 1 1 E11 C22 2 E12 plus C22 E13 plus C22 E21 plus C22 E22 plus C22 E23 plus C22 31 E31, okay, plus C22 32 E32 okay. Okay, now clearly we have to bring them to the same system. So C21 will be E11, okay, plus C22 will be E22, We're trying to get the strains over here written in this form. Okay, C23 will be equal to E33, right? C24 will be 2 times of E4, which is EYZ, and EYZ is 2 3 plus C25 is 2 times of EZX, which is 3 1, plus C26 is 2 times of E61, which is, sorry, it's not ZX, XY, yeah, 1 2. Okay, now this implies that C21 is equal to C2211. Okay, C22 is equal to C2222. C23 is equal to E33, C2233. Okay, and C24 is equal to E23. E23 should occur at two places. One is C2223 equal to E32, C2232. 2232. Okay. Similarly, C25 should be E31. So that would be C2211 equal to C2231, and C26 is equal to 1 2. One, two. E12. So E12 is okay. C2212 equal to E2 and C2221. Okay. So this, I think we can complete this at least. This is C2233. There is an error in your textbook. Okay, please correct that for this term. So this is correctly C2233. Okay, and then C24 is C2223 or 2234, 2223, and then C25 is C2231, and then C26 is C2212. Okay, so, and you can proceed by writing it all for the all rows. So the idea is this: in general, the elasticity, the two elasticity tensors stiffness tensors Cij and Cijkl, okay, are related, and related by this expression which you have over here. Okay. Okay. Now, just like the sigma ij equal to Cijkl ekl could be inverted, similarly, this expression sigma I equal to Cij eij can be inverted to write the strains in terms of stress, and you would again call this as the compliance tensor. This is from the Voigt notation matrix. So this is Sij is also a compliance matrix. Okay, and obviously it will also be related to the S. So Sij and Sij KL will also be related. So this is easy to do. Okay. Now, once we are done with this, let's take up the topic of material symmetry. In this particular topic, we see earlier we have claimed that there are certain directions where the elasticity tensors are, where the elastic response are same. Okay, what this means is that if you have, say, a coordinate system like this, x and y, okay, say for this material, simple cubic, okay, the response along the x direction will be the same as the response along the y direction, meaning if you transform this coordinate system such that this is your x dash and this is your y dash, then the elastic response along x is the same as elastic response along y. Okay, so the under this particular transformation, clearly this transformation is a rotation of this coordinate axis along 90-degree counterclockwise. The elastic response along Ex and Ex dash will be same. Similarly, if this direction was x, okay, and then now you transform so that this direction becomes x dash. So in this case, x and x dash will have the same elastic response, and so will this x double dash. Okay, so clearly once you have a rotation like this, the other you have a rotation of this value. Okay, so we want to now put this idea that the elastic response is same using the transformation matrices which we have learned before. So let's call this material symmetry. So we will use the non-contracted form over here. Non-contracted form because it is easy to apply the transformation laws. Now non-contracted form is essentially this one. Okay, so sigma ij dash is equal to Cij KL dash. So okay, so this one. So we are not using this, just because applying this transformation law is easier in this form. Okay, so let's see. In the original system, okay, and I am considering this case just for the case of simplicity. Okay, let me show it with red. This direction. Okay, so in the original system, you will have sigma ij equal to Cij KL EKL. Okay, now in this any transformation, say this purple, you can write in the new system, new coordinate system, sigma ij dash. So this is a dashed coordinate system, Cij KL dash EKL dash. Okay, so this would mean that the stress, since it is a tensor, okay, it will transform according to this law. Okay, similarly the strain will also transform according to this So this is a general transformation which is happening. Of course, it's a three-dimensional. I'm showing you a picture of a two-dimensional, but what we are doing is a truly three-dimensional. Okay. Since stress is a tensor, it follows this transformation law. Since strain is a tensor, it follows this transformation law, and it also follows the inverse law, in which case the purple is the old coordinate system and red is the new coordinate system. So in that case, you would have sigma ij is equal to q ki q lj sigma dash kl qki qlj e dash kl ki qlj e dash kl. Okay, fine. So this is the purple to the red, purple to the red, red to purple, red to purple. Okay, so these two exist because stress and strains are tensor. Okay, now if you combine this one, okay, and this one, let's see, combine this with this and use the conditions which we had learned earlier. I think we had also used it somewhere in the discussion on stresses. So they were, if the transformations are orthogonal, which they are in our case, then they must have these properties, which is qji qjk is equal to delta ik and qij qkj is equal to delta ik. Okay, these are the properties of the orthogonal transformations. So if the transformation is orthogonal, then it follows this these properties. Now combining this and this, okay, we should be able to get this. So this dash every time I apply is clearly on the sigma or the C, not on L clearly, okay. Q J N Q K P Q L Q C M N P Q. Okay, let's see and try to see at least how we can do that. Okay, so Cij dash is equal to Q I K Q J L sigma KL is equal to Cij KL dash EKL dash is okay. Now we want to sort of arrive at this finally. So how can we do that? Sigma KL I think is something which we can play with. So sigma KL or EKL dash, sorry, EKL EIJ dash is equal to, let me discuss the way. I think this is a time when you should be able to do these simple things. Try to write it over here, okay, and then try to write this using sigma ij equal to Cij KL EKL. I am guessing that at some stage you should have this situation where you can say that for any arbitrary strain you should get this. So how would you do that? Let's see. Here I want to replace KL. Okay, so I'll replace I with M. Okay, so sorry, this would be Q K M Q L N E K L. Okay, and similarly sigma KL can be written as sigma KL is equal to C KL MN EMN. Okay, so QIK QJL CKL MN EMN is equal to CIJKL dash QKM QLN EMN. Okay, so at least EMN is common. Okay, now QIK I'm just trying to do, but I think you should be able to do this on your own if you try it. Oh, this was dashed. Okay. So now you have to throw out this QL so on this side. So clearly if this is valid for any arbitrary strain, this would only mean that CIJKL dash QKM QLN is equal to QIK QJL CKLMN. Okay. Now, what is the way? Obviously, using this. Okay, you can take it on the other side. So let me see. JI. So think about this. I think this is something which you can verify. If you like this, you can proceed it in this form. If not, I think it is a good exercise for you to figure out. If there's any doubt, please feel free to ask me. Okay, so I'll write this final form, which is CIJKL dash is equal to QIM QJN QKP and QLQ CMNPQ. Though we have tried to do as the authors wanted us to do, however, you can also use this transformation law, okay, because CIJKL is a tensor, it must follow this transformation law under any transformation, okay. So if you know what the transformation law is, Qij, you can just use that over here and find this changed CIJKL dash or the transformed elasticity tensor. Okay, but if under this transformation CIJKL is equal to CIJKL dash, meaning the response along the red direction and the purple direction are the same under this transformation. So Cijkl will be the same as Cijkl dash. This would mean that you will have Cijkl is equal to Qim Qjn Qkp QLQ and CMN PQ. Okay. So this is under this specific transformation only, not for a general transformation. Okay. Now because of this property, there will be a reduction in the number of elastic constants. So Cijkl has 21 until now. Because of this symmetry, depending on the kind of symmetry, this number will keep on reducing. So let's see the first case. Let's call it the plane of symmetry, or the so-called monoclinic material. So if this is your x, y, or sorry, let me call this as z. And if the plane of symmetry is along this xy plane, okay, xy plane, then what would happen is that the transformation matrix should look like this. Okay, so basically any vector which is like what, so 2 I cap plus 3j cap plus 4k cap would become 2I cap plus 3j cap minus 4k cap. Okay, so they will be all symmetric, and this transformation law will help you do that. Okay, you want to see this? Okay, let's do that. 1 0 0 0 1 0 0 0 minus 1. I'm just doing it for a vector just because it's easy to do. So 2 3 4, this will become 1 2 3 minus 4. Okay, so this transformation is a symmetry about the xy plane. So similarly, if you had symmetry about the yz plane, you would have, I'm guessing, minus 1 0 0 0 1 0 and 0 0 1 and so on. Okay, so we are taking just this one example of this xy plane being the symmetry. Okay, now one of the things, and this you can also do it for a vector, sorry, a tensor. I'm just not doing it for now because this was an easy calculation to do, but this is the idea. Okay, let me now remove this. One of the things about this transformation is that it's not actually a right-handed coordinates transformation. Okay, so it is not a proper orthogonal transformation in the sense it does not preserve this rule. See, in this diagram, if you use your right hand thumb rule, x cross y will point in the z direction, which is correct. Okay, but this particular transformation law does not preserve that. However, this will work for our investigations of symmetry, so we will continue using it. Okay, this transformation law is what we'll be using despite that fallacy which we have pointed out. Okay, now what we want to do is we want to substitute this transformation into this one. Okay, so let's see how we can do this. Okay. Cijkl is equal to Qim Qjn Qj n Qkp Qlq Cmn Pq. Now, once you put this over here, you will be able to see thatCijkl is equal to minus ofCijkl if index 3 appears odd number of times. Okay, like once or thrice. Okay, now we want to check this claim. Okay, of course there are many ways to do it, but we are taking the easiest way of checking. So let's pick out a C which has the index 3 appearing odd number of times. So this cannot be, because here it's appearing twice. This can be, and this cannot be. This cannot be because it appears twice. This cannot be, and this can be, this can be. Okay, this cannot be. So let's take up a case in which it is appearing odd number of times. Let me just take out this C1131. Okay. So let me just take C1131. Okay. Okay. This would mean that Q1M, Qj is what, 1, N, Qkp, K is again 3, right? 3p, and Qlq is 1q, Cmn pq. Now we want to expand it along with 1. Do keep in mind that this is also, so Q11 is equal to 1, Q22 is equal to 1, Q33 is equal to minus 1, and every other Qij is actually equal to 0. Okay, based on this. So we just want to keep the ones which are non-zero. So let's see, if m is equal to 1, okay, what are the terms which will give non-zero? M equal to 1, okay, and n is equal to 1, okay, and p is equal to 3, but this will give a minus sign, okay, because Q33 is actually equal to minus 1, and again Q will be equal to 1, okay. This would imply that you will have 1 into 1 into 1, sorry, 1 into 1 into minus 1 into 1 into C1131. This would give you minus of C1131. This implies, now if you take C1131 on the other side, 2C1131 is equal to 0. This implies that C1131 is equal to 0. Okay, soCijkl is equal to minus ofCijkl if index 3 appears odd number of times. Let's take up another C where it appears odd number of times. Let's take up C3333, okay. I mean, I can also take I can take C3333. Let's see. No, but this is not an odd number of times, right? We need an odd number of times. That is okay. So let's we have already actually shown it for an odd number of time, which is once. Okay, and let's try to show that if it occurs even number of times, then this is not true. So C1131, let's try that. 1133, sorry. So C1133 will have what? Q1M, Q1N, Q3P, Q1Q, sorry, Q11, so this will also be 3Q, and CMN PQ. For the non-zero terms, M will be equal to 1, and n will be equal to 1, and p will be equal to 3, and q will be equal to 3. Okay, this will give a 1, 1, minus 1, minus 1, and this will make it a C1133, but this product will be 1, so C1133 equal to C1133. So there's no minus sign over here. So because 3 is appearing even number of times. Okay. So this statement is correct. You can also do it for many other steps, or you can do it in the lengthier way and perhaps prove it in some more fashionable way. But the idea is that this statement is verified now. Okay. Now if, so let me just write, this givesCijkl equal to minusCijkl. This implies that Kijkl is equal to 0 if index 3 appears odd number of times. So what are the terms in which the index appears odd number of times? Let's see, let me remove all this. Let's see, sorry. Two, three, 2, 3. Okay, so index 3 appears odd number of times, so that index has to be equal to 0, meaning this is 0, this is 0, this is 0, this is 0. Okay. Okay, and yes, fine. So if you see all these three things, so let me just put out one more number, C3323. Okay, this is also 3 appearing odd number of times, C3331, C3312, C2323, C2331, C2312. Okay, so this is appearing odd number of times, odd number of times, odd number of times, not odd number of times. Okay. So is it correct to say that C14 is equal to 0? It is correct. C24 is equal to 0. C34 is equal to 0. Then C15 is equal to 0. C25 is equal to 0. C35 is also equal to 0. And C46 is equal to 0. Okay, and then there's one more term which is hidden, C3112, this is also 0, and C56 is also equal to 0. Okay, so a lot of these terms have become 0. Now this means that what we have just written over there in red, you should verify that this can be written that Ci4 is equal to Ci5 is equal to C46 is equal to C56 is equal to 0 for I equal to 1, 2, 3. Okay. So this would mean that this elasticity tensor, okay, this will take the form C11, C12, C13, 0, 0, C16, C22, C23, 0 0 C26 C, sorry, this is just symmetric, so I'm just putting a dot. 0 0 C36 Okay, so this is what we have reduced our elasticity tensor to. Okay, and what have we done? So we had these 21 constants, we boiled them down to 13. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so now the number of constants which we have come down from 21 to 13 because of this plane of symmetry, which is the xy plane, just one symmetry plane. Now if you have three perpendicular symmetry planes, which is a orthotropic material, this is the class of material which is like a bone or wood, very commonly classified as orthotropic material. Okay, now how do we have to proceed? First of all, you should be able to visualize what the three planes are. So if you have z, if you have x, if you have y, so the first plane of symmetry is clearly this xy plane. The second plane of symmetry is clearly this yz plane. Okay, and the third plane of symmetry is clearly this xy plane. Okay, so you have three mutually perpendicular planes of symmetry in a material. This so how do we further reduce this? So what we have already done, if you notice, that we have already taken the xy plane as the plane of symmetry and then seen what happens to the elasticity tensor. Okay, what we can do is, over and above this, we can do a 180-degree rotation. Okay, and then we can do the same rotation again and again over this. Okay, so let's start with this form. Okay, since some part of the work is already done, and over this you apply the symmetry plane, which is yz plane. Okay, now if yz is the plane of symmetry, then qij would look like minus 1 0 0 0 1 0 0 0 1. Okay, if yz is the plane of symmetry, the red plane, yz plane, sorry. So you have to now again sort of repeat the same idea. What do you have to do? You have to again apply this Cijkl is equal to Qim Qjn Qkp Qlq Cmn Pq. Okay. In this case, you will get C26, C36 and C45 equal to 0. Okay, how would you do that? Let me just show you the other way. Let's take up C45, or let's take up C26. Okay, so C26 is actually equal to, if you look at the expanded form, C26 is equal to C2212. Okay, and let's see that. So C2212 is equal to Q2M Q2N, sorry, Q1P Q2Q C MNPQ. Okay, again we want this to be having non-zero values, so M will be equal to 2, N will be equal to 2, P will be equal to 1 and Q will be equal to 2. What will each do? C22 is equal to 1, C22 is equal to 1, C11 is equal to -1 and Q22 is equal to 1. So this would mean that C2212 is equal to minus of C2212. This can only mean that C2212 is equal to 0 or C26 is. Okay. So that's how you can verify this, all of these terms, that for if you apply this particular symmetry plane YZ, you will now get this one. Okay. Now this would further reduce your elasticity tensor to C11, C12, C13, 0, 0, 0, C22, C23, 0, 0, 0, C33, 0, 0, 0, C44, 0, 0, C55, sorry, this is C55, 0. Okay, so we had 21 to 13 earlier, and how many of them are right now? They have 9. Okay, you can see this and see that there are only 9 independent constants. Okay, so after this, obviously there is one more plane left out, which is the XZ plane. Okay, so if you repeat this, in the sense, take this as your starting elasticity tensor, now take the XZ plane, you will find no new results. Okay, meaning they will all be identically satisfied. The transformation law which you have over here, this will be identically satisfied for all. So you will not get this minus thing which we have been getting. Okay. And this is a case in which you can see that even though a third symmetry exists, it's not helpful in reducing the elasticity tensor. I mean, it will remain the same even if you apply. Obviously, you could have started with any plane of symmetry and taken the next one, so you would get the same answer in either ways. Okay. One of the other quotes which you have is that about this orthotropic material. So now you have this elasticity tensor for a nice orthotropic material. Okay, so let's write it down nicely. Sigma 1, sorry, C11, C12, C13, 0, 0, 0, C22, C23, 0, 0, 0, C33, 0, 0, 0, C44, 0, 0, C550, and because the dots are basically the symmetric terms, so not independent. And this you would write as what? Sigma 1, sigma 2, sigma 3, or okay, so that would mean, let me just use the XYZ notation, which is sigma x, sigma y, sigma z, tau yz, tau xy. This would be ex, ey, ez, 2 eyz. Okay. Now, if you look carefully at this relationship between stress and strain for an orthotropic material, if shear strain is equal to 0, this implies that shear stress is also equal to 0. Okay, this implies that the principal axis of stress and strain more axes are there, right? Of stress and strain coincide. Okay, so this is again because the shear strains and stresses are all coming out to be 0. So this, for 0 shear strains you get 0 shear stress. So that would have no other option to verify to have a principal stress which is principal axis which is different from each other. This is obviously not true for a general anisotropic material. Okay. You can also write the compliance matrix in the sense if you invert this relation, sorry, if you invert this relation, you should be able to get a compliance matrix. So Sij is equal to 1 by E1 minus nu2 1 by E2 minus nu3 1 by E3 0 0 0 minus nu1 2 by E1 1 by E2 minus nu3 2 by E3 0 0 0. Again, symmetric terms. sorry. So this is dot 1 by mu 3 1 0 1 by mu 1 2. Okay. Obviously, EI are the Young's modulus, Young's moduli in three directions of symmetry. Okay. Nu ij is the Poisson's ratio, which is defined by minus Ej by Ei for stress in the I direction. Okay. So if you had say nu 2 3, that would be equal to minus E3 by E2 when the stress is applied in the 2 direction. Okay. And similarly you will have a mu ij, which is the shear modulus in the ij plane. Okay, since there is a symmetry over here, okay, compliance matrix and is also symmetric, just like the elasticity. So this term is equal to this term, and this term is equal to this term. So this would mean that nu ij by ei is equal to nu ji by ej. Okay. So this is all we can say, and this, if you have done or are doing any course in composites, you would find these symbols very oftenly used over there. Okay, so these notations are coming from the isotropic theory, but they have their own meaning, as you see over here. Okay, so both this compliance form and the elasticity stiffness tensor form are useful. Normally, when we study composites, it's this form which we would want to use. Okay. Okay. So one can also have an axis of symmetry. I mean, we have discussed these directions of planes of symmetry: one plane, two planes, three planes. Even though the third plane of symmetry, which because it was mutually perpendicular, didn't really add anything to the reduction of numbers. So, but right now we had come from 21 to 13 and 13 to 9, okay, with three planes of symmetry. Let's see what happens when there is an axis of symmetry. It is also called transversely isotropic material. Okay, in the transversely isotropic material, we have a symmetry with respect to the rotations about an axis. Okay, so this is something new and different. I mean, until now we were referring to symmetries about a plane. Now we are referring to rotations or symmetry due to rotations about an axis. So assume that you have this x-axis, you have a y-axis, and then you have a CIJKL or CIJ, whichever form you would want to write, and that's there. Now if you rotate this system to this purple system, okay, and then you should have this purple CIJKL now, which is this transformed elasticity tensor. And the idea is that after this rotation of angle theta, this purple should be the same as the black one. Okay. Now this is for this one particular theta. okay, and you can imagine that you can have lots of thetas over which this symmetry can hold. For example, if you do a rotation by an angle theta which is equal to 2 pi by n, okay, n is an integer, so you use the language that the material possesses an axis of symmetry of order n when the elastic moduli remain unchanged for rotations of 2 pi by n radians about the axis. Okay, so of course in this transversely isotropic we are referring to only one axis, in this case the z axis, which about which the rotation is happening by an angle theta, and then you say that it possesses an axis of symmetry of order n, okay, where the rotation has happened by theta equal to 2 pi by n. Okay, now we'll take up a few n's, in fact a couple of n's, just to see how this plays out. Okay, so first let's take the easiest n, which is n equal to 2. Okay, that means the rotation has happened by pi radians. So you can imagine that if you have an x and y, your x dash and y dash is written like this. Okay, and you are supposed to say that the elasticity tensor values remain the same under this transformation. Okay, so if you want to write this qij for this would come out to be cos theta sine theta 0 minus sine theta cos theta 0 0 0 1. We have studied how this comes out. You have to see the cosine of the angle between say x and x dash for this case, and so on. Okay, cosine of the angle between z and z dash is this one. Okay, if you substitute theta equal to pi, you would get this as minus 0 0 0 minus 1 0 0 0 1. Okay, now if the transformation relation now isCijkl is equal to what? Qim Qjn Qk P Ql Q Cmn Pq. Okay, so let's take up and if you put all the values under this transformation, you will be able to get, say, C1 I4 equal to CI5 is equal to C4 6 equal to C5 6 equal to 0, where I is equal to 1 2 3. The reason this would happen, because a rotation of theta equal to pi would means there's a symmetry about the original y z plane. Okay, so that is what will happen, and then this is just the same as the symmetry of a plane. So reason, I mean, we can just see a couple of these cases. Ideally what you should do is you should go to this value. Where did it go? you should go to, sorry, where did we write the, okay, here it is. So ideally you should put out this value. So let me just see if I can cut this out. No, not this one. You should take out each one of these values and put it under the transformation. Okay, and then copy. Okay, let's see how it looks like over here. Okay, good. So let me just remove some of these terms. The red ones let me remove. So this is 3312, and then you have 332, 33331, 3312, then 2323, 2331, and 2312. C3131 is equal to C3112, C1212. Okay, so you have to put all these terms under this transformation and equate them, meaning if you just look at, say, C I don't know, 1 5, okay, because that should be equal to 0. So let's put C15. What is C15? It is this one. So we want to write C1131, and it should be equal to C11. I'll use a purple color, okay, because after transformation it should look like this. And then I will write Q11, Q11, Q33, Q11. This is equal to minus of C1131. Okay, reason is Q11 is equal to 1, Q33 is equal to, sorry, Q11 is equal to minus 1 over here. Okay, and Q33 is equal to 1. So you can directly write. So this method will actually work well if you have only ones and minus ones in your transformation matrix. Okay, please don't try to use it, because you should know that what this actually means is a summation. Okay, so there's a summation implicit in writing this form. So I am not doing that over here because I have one. So this is just like a delta function which we used to say, and we would easily claim that for the non-zero values we would be able to write this, and hence it would retain the same form. So this would mean that 2 times of C1131 is equal to 0, or C1131 is equal to 0, or C14 is equal to 0. Okay, and similarly you will find lots of these values would be equal to 0, and this would be the exact same form which you had before. Okay, so out of 21, how many have become 0? Let's put a mark. 1 4 is 1 4, this one, then 1 5 2 5 3 5. Okay, 4 6 is this one, 5 6 is this one. So out of 21 independent constants, we have 8 of them as 0, so we are left out with 30 independent constants. What it means is that if you have a rotation about an angle about the axis z in the by pi radians, you will have only 13 independent constants. Okay. Now let's take up a case of say theta is equal. I'm just taking the easier cases because I want to demonstrate up something. Okay. Ideally, you can just take any angle. Okay. You can take theta is equal to, I don't know, 23.7 degrees. Okay. And then coincidentally, you will be able to write what qij would be. Just substitute it over here, and then you would have the transformation relations. Okay. You would have the new Cijkl in terms of the old one. That's not a problem. Okay, but I'm trying to demonstrate some easier cases so that I don't have to go through that lengthy summation. You can imagine how many summation terms this would have, because each of this will be summing over say m, n, p and q. Okay, so let's take up n is equal to 4 for a moment. Okay, that would mean that the rotation is about z axis by an angle theta is equal to 2 pi by 4 equal to pi by 2 radians. Okay, that would mean that qij is equal to, again, cos theta would be what? Cos pi by 2 sine pi by 2 0 minus sine pi by 2 cos pi by 2 0 0 0 1. This would make it 0 1 0 minus 1 0 0 0 0 1. Okay, and over here, as you can see, that you still have ones and minus ones only, just because I was very clever to take a suitable n. I mean, if you take n is equal to 3 or 6, you don't have this privilege, and then you will have to expand it in the full form. So I'm just taking these forms because it is easier to solve this transformation relations. That's all. Okay. Okay, so let's see what this does. Very clearly, you can see that q11 is equal to 0. Not q11. Let's just write the non-zero terms, which is q12 is equal to 1, q21 is equal to minus 1, and q33 is equal to 1, and then qij is equal to 0 for everything else. Okay. So let's take up a few relations and see what we should have. First of all, I am giving you the answer. Okay, I mean, the way to go about is, again, you go one term by one term and then you will find certain relations. So let's do that way once rather than writing the relations first. Okay, so let's write, I don't know, Cijkl is equal to q1, sorry, qim qj and qkp ql qcm and pq. So c1 1 2 3. Okay, I mean, it is not random. It's the sense that I have to do this for all these numbers anyways. Let me just remove this sign. Okay, so I just C1 1 2 3 is this one, which is C1 4. Okay, so this is C1 4, and this should be, according to this transformation law, be equal to what, 1m q 1n q 2p and q 3q cmnpq. Again, ideally we should just be expanding it across m, n, p and q, and each of m and p will take a value of 1 2 and 3, so it's a lengthy expansion to take care of. But because we have these ones and minus ones only, so we want to see what will be the non-zero value, just like the delta functions which we used to do. So if you look at this term 1m, the only possibility with 1 is that it should be 2. So this should be q1 2. Okay, otherwise it would be 0. Okay, and then q1n would again be 1 2. q2p should be 2 1, because if there is any other 2p like 2 2 or 2 3, it would be 0. That's not what we want. So we write it as 2 1, and then 3 3 is again the non-zero quantity. That would give us what? That would give us these. That would be 2 2 1 3. Okay, and what would this value be? This was 1, this was 1, this was minus 1, and this was 1. Okay, so this would be minus of C2213. Okay, so C2213 is there. Now C2213, let's see where it is. Can you see that this is C2213? C2213 is equal to C2231. Okay, you know this property where this and this can be interchanged. This was due to the symmetry of the strain tensor. Okay, so that's why I can write C2213 as same as C2231, and that is C15. So what this relationship gives me is that so this is C25. It gives me that C14 plus C25 is equal to 0. Okay. Now let's try to reverse it. Let's see what this gives us. Let me see what this should give us. Let's try to do a C2213. That should give me Q2M, Q1N, Q21, Q1P, Q3Q, CM and PQ. Now again, only possibility is that this becomes a Q21, this becomes a Q21, this becomes a Q12, this becomes a Q33. That would give it C1, C1, C2 and C3. Okay, and this would give you actually 2 1 is minus 1, 1 2 is 1, and 3 3 is 1. So this should give us C1 1 2 3. Okay, so C2 2 1 3 was C25, and this is C14. So this relation gives you C14 is equal to C25. Okay, now for both of them to be true for this one, and because both of the transformation relations are correct, okay, the only possibility is that C14 is equal to C25 is equal to 0. Okay, so this is the way to go about it, and then you can take perhaps the next set of numbers. I mean, there are 21 only. Okay, please don't misunderstand this. When you start with n equal to 4, you should start with this fresh set of 21 independent constants. Don't take it as something else. Okay, don't already reduce it to 13 and then further go for this. That's not what you are doing over here. This is a fresh set of n equal to 4, or rotation about pi by 2. Actually, I have drawn this wrong. This is x dash and this is y dash. And over here, you have this as x, this as y. Over here, you will have this as x dash and this as y dash. Okay. Okay, so you would do all this, and let me now write out what will happen with many constants. Please proceed in the same way, okay? There's no other way to prove zeros. Remember how the zeros have come up in the earlier case. Zeros had come up becauseCijkl was equal to minus ofCijkl. In this case, we have done it in a different way. I mean, just because the transformation law was like that. And again, we have been very careful to choose nice transformation angles. If it was anything other than this, then you would require you would be required to expand the expressions and then move ahead. Okay. So this is what you would get if you follow this method. So I have just done it for one. You can proceed and say do it for other values as well. Okay. So let's see. So how many are 0? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So you would have these values is equal to 0. Okay. And there will be some other expressions as well other than the 0, and let me see if I can prove that to you. Okay. Let me just other than this you will also have C22 equal. Other than this, you will also have C22 equal to C11, C23 equal to C13, C55 is equal to C44, and C26 equal to minus of C16. So I would have loved to prove all of them, but let me just, so I've already shown to you how one of the zeros is proved. Let me now try to prove this. C26 is equal to minus C1, and this is something which you will automatically get. So let's see what C26 is. C26 is 2212. So I will write it as C2212, and this is equal to Q2 M Q2N Q1P Q2P CMNP Q. Again, this has to be Q21, Q21, Q12, and Q21, and this is C1121. So 1121 is this value, right? Because this is equal to C1121 because of the symmetry of the KL and LK. So C16. So this would be equal to minus of C1121, or C26 is equal to minus C16. Okay, so this is this particular property. Okay. Let me just prove one more just for the sake of completion. Let me try this. C22 equal to C11. So let's see what C22 is. C22 is quite simple. C2221. Okay. So I will have C2222 equal to Q2 M Q2N Q2P Q2Q C M N P Q. Okay, now obviously only possibility is this, and all of them Q21 is actually equal to what? Minus 1. So 4 times minus 1 would be equal to 1, and hence it would be this. So this proves that C22 is equal to C11. Okay, so similarly all these will be proven. So now let's count out, since we now have the complete set. Again, I mean, I'm not doing all of it, but you know now how to go about it. I have written the answer first and then proved, but ideally I should have proved everything. But I think you get the method. Anyways, so there were 21 originally. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 are proven to be zeros, and then there is a relationship between the remainder. So 10, 11, 12, 13, and 14. So you had 21 minus 14, only 7 independent constants. Okay. So what did you observe over here? When you took n equal to 2, you had 13 independent constants. You have n equal to 4, you will have what does we just calculated, 7 independent constants. Okay. Okay, so it seems as the angle keeps on increasing, n keeps on increasing, and hence this angle of rotation 2 pi by n keeps on decreasing. So originally you took an angle of pi and then pi by 2. So depending on your angle of rotation, it seems the number of independent constants are decreasing. Okay, and I'm stating without proof that if you take n equal to 6, okay, you will have 5 independent constants. The way to go about it is the same. You please find theta equal to 2 pi by 6, which is 30 degrees. Find a transformation matrix and put each term into this relation, expand it, okay, and then you should go about it. I'm not doing this because it would be lengthy, okay, because you don't have ones and minus ones anymore as soon as the angle is not pi or pi by 2. Okay, okay, so this is the case, and obviously all of it is there for rotation about z axis, right? Always remember this. Now it does happen that if you rotate it by theta equal to 2 pi by n, where n tends to infinity, you still get only 5 independent constants. Okay, so without proof I am stating that n equal to 6 case corresponds to n tending to infinity case. The method is still the same. You apply by 2 pi by n, write it, and apply the limits later on. Okay, and then you will still get 5 independent constants. Okay, now that would look like this. Which case? The n tending to infinity or n equal to 6 case. Okay, so this is the so-called transversely isotropic material about a rotation happening at a very small angle. N tends to infinity is a very small angle. So let's see physically what's happening. And okay, you have an original coordinate system and you have a Cij KL into that one. You rotate it by a very small angle theta. Okay, since 2 pi by n is theta and n tends to infinity, so theta would automatically tend to 0. But don't do the mistake of just writing theta equal to 0 in this the transformation matrix, because you have to take that limit in the expression. So this is your new axis, very small theta, and this is equal toCijkl. Because of this symmetry, and the elastic tensor in this very small theta should remain the same. Okay, and from this theta, this new theta, you can take another very small rotation, and this value will also remain the same. Okay, from this green theta, take again a very small theta and find theCijkl, and they should also be the same. So this is what is happening. This would imply, and you can keep on doing this until you sweep the entire 2 pi angle. Okay, what would mean is that no matter by what angle theta you rotate,Cijkl remains the same about z axis. Okay, this is one of the important things, that it is only about the z axis. So no matter what angle you, because the previously gotCijkl, which would be a differential angle theta, would be the same, and so you can sweep basically the entire 2 pi angle like this. So this is the physical interpretation of this. Okay, and in composites, for example, if you have, sorry, let me just, if you have fibers in a composite like this, okay, you can draw your x, you can draw your y, you can draw your z, and then you keep on rotating this about this z axis, you will get the sameCijkl, or the elasticity tensor. Okay, that is what a so z axis here is the axis of symmetry for a transversely isotropic material. Okay, now coming further to that, complete symmetry, or the so-called isotropic material. What would this mean? See, the previously applied symmetry was for all angles practically. I mean theta tending to 0 uh, for rotation about the z axis. Now over and above theta tends to 0 rotation about z axis, we have the same rotation about x and y axis, you would get a situation which is called complete symmetry, in which you could have basically rotated in an angle about any axis, or even combined them, and you would have still got the same answer. So just like the symmetry about the planes, you remember we have considered symmetry about one plane and symmetry about the second orthogonal plane, and then the third plane didn't contribute anything new. Similarly, you can do this by considering the symmetry ofCijkl with respect to two orthogonal axes. This implies symmetry about the remaining axis. Okay, so you have to now proceed over and above that one. Okay, and the method would remain exactly the same. So you start with this Cij which you have got over here. Okay, and then do a rotation about, say, I don't know, y-axis in n equal to 2, y-axis in n equal to 4, and then y-axis in n tending to infinity, and then you would be able to reduce this further. So you should verify this. And take the easier ones again. I won't make you work very hard for this. N equal to 2, n equal to 4 for rotation about, say, I don't know, y-axis. And then eventually it will be about 6 only, which will be the infinity case. Okay, so finally, after doing this, you should be able to get that okay. So this is the Cij which one should get, and as you can see that there are only two independent elastic constants. Okay, and you can actually write this form as we have seen this, I think, already. Lambda plus lambda delta ij, sorry, lambda delta ij delta kl plus mu delta ik delta jl plus delta il delta jk. Okay, so let's try one of them. Okay, let's see C111, this one. Okay, this should be lambda delta 11 delta 11 plus mu delta 11 delta 11 plus delta 11 delta 11. This is equal to lambda plus 2 mu, which is lambda plus 2 mu. Okay, and similarly you can say find this value, which is what, C1122, I'm assuming. Yes, C1122. So let's see, C1122 is equal to lambda delta 11 delta 22 plus mu into delta 12 delta 12 plus delta 1 2 delta 1 2. Okay, this would be equal to lambda because this would be 0 and you already have a lambda. Okay, so this is how you would be able to say there is a complete symmetry, and which we call as the isotropic material, which was actually the focus of our discussion throughout almost the entirety of this particular course. So now you have a new perspective to look at this symmetry. So just to summarize, I mean, we had 81 elasticity constants. Coming down to 36 was quite easy because of the symmetry of the stress and strain tensor. Coming to 21 was because of the presence of elasticity is a strain energy and density. Okay, now after this one could have taken a few routes. I mean, you could have come down to say the symmetry along a particular plane. If you take one plane, this would get reduced to 13. Okay, and then the second plane would reduce it to 9. The third plane would also reduce it only to 9, so not much advantage, and that had given the so-called orthotropic material, or orthotropically anisotropic, whichever one you would want to call. Then the symmetry could have been about a particular rotation about the z-axis, that for one case gave us what, how many, sorry, we had 13 independent constants. Okay, then we also reduced it to, so for this was n equal to 2, this was for n equal to 4, and this would have reduced to 5 for n equal to 6 or n tending to infinity. Okay, this was I'd stated without proof. Okay, now if the same thing was repeated for another axis, this would have reduced to 2 independent constants, and for the third it would have also reduced to 2. So this was called transversely isotropic, and this was called isotropic. Okay, so this is what we have done, I mean, so far, give or take, most of this course. One of the last topics which we would want to deal with, at least just simply by mentioning it, is again the restrictions on the elasticity in elastic moduli. So we had already learned about these restrictions in an isotropic case, but since we are in this anisotropic domain, we should also just go about and see how this happens. So there are two ways to do this. I mean, remember the earlier case we used to do some sort of tests, uniaxial test, pure shear test, and hydrostatic test, and so on, and then we would be able to give bounds on the nu and e. Okay, that would give some sort of restrictions on the elastic moduli for an isotropic case. For anisotropic material, there are two methods to go about it, and each would give you a different answer. One is the so-called rotational invariance. I will explain both of them. And the other is the positive definiteness of the strain energy. Remember, for isotropic, we have already used this argument before. Okay, if you have a doubt, please pause the video over here and go back and check. So let's see what this rotational invariance means. So we're demonstrating one case of rotational invariance. So apply a rotational transformation about z-axis. That would mean you apply this qij equal to cos theta sine theta 0 sine theta cos theta 0 0 1. Okay, and with this case we can show that C44 dash in the transformed transformed elasticity tensors are actually equal to C44 cos square theta minus 2 C45 sine theta cos theta plus C55 sine square theta. How would we do this? I mean, just apply this transformation law. PQ, okay, and you would be able to get this. Similarly, C55 dash would be equal to C44 sine square theta plus 2C45 sine theta cos theta plus C55 cos square theta. Okay, now if you add this and this, you will get C44 dash plus C55 dash is equal to, so this term and this term will get cancelled, and cos square theta plus sine square theta equal to 1, so they would get C44 plus C55. So this is the so-called rotational invariance. You didn't assume that this so 44 dash would be equal to whatever you have on the right hand side over here. Okay, we had done that before because we were using symmetry arguments. This is not a symmetry argument. This is saying that the quantity C44 plus C55 will remain invariant under any transformation. Just like for the stress, if you remember sigma 1 plus sigma 2 plus sigma 3 or sigma xx plus sigma yy plus sigma zz, this was invariant. I think the first invariant divided by 3 multiplied by 3, I'm not sure. But yeah, so so I1 was equal to sigma k divided by 3. Okay, so this was 3 times the invariance, and this 3 would remain invariant, and hence I1 would remain invariant. So similarly, you have this sort of relationships uh, and restrictions over the anisotropic elastic moduli. So the summation of C44 and C55 will always be the same under any rotation angle about z-axis. Okay, so we have shown you one example. Many such invariants exist. So let me mention. I mean, the first one obviously very proudly we can write because we have shown that. Okay, this is something which you should verify. Please do this. Okay, verify that you can actually write C44 dash and C55 dash using this. Okay, you have to use this theta only. I mean, you don't have a value for theta, so unfortunately you will have to do that, and it won't be really lengthy. At least one of these you should do. So C44 plus C55 is an invariant. C66 minus C12 is an invariant. C11 plus C22 plus 2C12 is an invariant. C44 plus C55 is an invariant. We have already written that, so let's not write that again. And C13 plus C23 is an invariant. C34 whole square plus C35 whole square is an invariant. C11 plus C22 plus C33 plus 2 times of C12 plus C23 C13. Okay, so these are a few of them which you can which I have written without showing. We have shown one. Now the other concept which we had learned was about the elastic bounds using the positive definiteness of the strain energy concept. Okay, so we will be able to write, I am stating all this without proof at the moment. Okay, the idea is very similar to what you would write about the strain energy. So U, if you remember, was equal to half sigma ij e ij, or half sigma I e I. Sigma I would be written as C I J E J E I. Okay, and then obviously there would be bounds about, because the strain energy U is greater than equal to 0, and you can show certain bounds about this Cij. So without proof, I am writing that for orthotropic materials, remember there are three planes of mutually perpendicular planes of symmetry, and you had what, 9 independent constants. You would get C11 C22 greater than C12 square, C22 C33 is greater than C23 square, C33 C11 is greater than C13 square. You would also get C11 C22 C33 plus 2 C12 2 C23 C31 greater than C11 C23 square plus C22 C13 whole square. Okay, for transversely isotropic, okay, meaning you have isotropy, angular isotropy about one particular axis. So you would have 5 independent constants, and the same argument would throw up these relations. I mean, you can clearly see what the form would be, right? I mean, we have already written that. Say for transversely isotropic, you have this form, right? Just substitute is equal to half into what, Cij Ej Ei. Okay, this Cij has to go in over here, and then just apply this expansion. So I and j over here can go from 1 to 6. Okay, so you would have a lot of terms, and then just substitute each one of them, and yeah, I mean, the strain square term would always be positive, and you should be able to come out with a few of these relations with some help from the linear algebra, especially about the eigenvalues and so on. Okay, and just for the isotropic case also, this would give you lambda plus 2 by 3 mu is greater than 0 and mu is greater than 0. So this is something which you have derived before. And why are you not getting any new result? Because the reason you had the logic which you had used earlier was the positive definiteness of the strain energy density, and you are doing exactly the same thing over here, so you cannot expect a new answer. You are just using a different sort of method over here because you started off with a more generalized form. But of course, I mean, if you just start out with this particular form, you get the exact same result. Okay, so this completes our so-called discussion on the restrictions on the elastic moduli. And for the purpose of this course, we will only be stopping over here. Okay, this is where we stop, and because the concepts which are not being done are somewhat advanced, and if you are more enthusiastic, perhaps in your related to your projects, you should find some other courses to study them or study them on your own. So I hope you had a good experience learning this course. Thank you.